Bismillahirrahmanirrahim. Assalamu alaikum. So for given function or given adapted stochastic process from the space of adapted stochastic processes, we have defined its Ito integral, I mean this quantity, in the previous videos. So we want to present some properties that are satisfied by this Ito integral. Number one, it is linear. In other words, if you are computing the Ito integral of linear combination of two adapted stochastic processes from this space, then it turns out that this is equal to linear combination of the Ito integrals of the functions. In other words, it satisfies the linearity. Secondly, the expectation of the Ito integral of any given adapted stochastic process is equal to 0. Third thing is variance of the Ito integral of adapted stochastic process, that can also be said that the square of the expectation of square of the Ito integral is equal to the quantity or the integral a to b of expectation of f of t square dt. So these are three nice properties which are satisfied by the Ito integral. Of course, we also have the expectation of the product of Ito integrals of two functions like f of tw dbt times a to b, another process g of t dw or w dbt. This is equal to a to b expectation of integral a to b expectation of f of t g of t dt, right? So that's also the property that is satisfied by this Ito integral. Thirdly, the Ito integral as a map, Ito integral I is a map from this L to AD omega to L2 of omega. This as a map is isometry, so it's an isometry. So what is an isometry? Refer to metric spaces, you will come to know what is an isometry. So these are some of the very nice properties of the Ito integral. If you want to know the proof of any of these, you can just comment down, then we can discuss, because we can't go into depth for these here, but if needed in future we will be providing the proofs one by one. Then in the coming lectures we will be looking at some of the Ito integrals. We will be computing Ito integral using the Ito lemma that we will define later. With the help of Ito lemma, we will come to know that if we want to compute the Ito integral of the stochastic process f of t comma w, let's say now I'm fixing a function which is Brownian motion itself. So I want to compute the Ito integral of this Brownian with respect to Brownian. So it turns out that this is equal to 1 over 2 the Brownian computed at b square minus Brownian computed at a square minus b minus a, this bracket. So we will come to know that Ito integral of this Brownian with respect to Brownian is given by this expression. We will also calculate in the coming lectures that the Ito integral of, we will also see that Ito integral of square of Brownian motion, Ito integral of square of Brownian motion with respect to Brownian motion. By the way, some books keep w of t in place of this Brownian, so that makes sense. So that can also be written. So here will be W, here will be W, here will be W, here will be W in place of B. So Brownian is represented by B, R, and some books by W. So there isn't much difference. You can treat them as same. So which is equal to 1 by 3 Brownian at A cube minus Brownian computed at B, Brownian computed at A cube minus integral A to B Brownian with respect to dt. So this Ito integral is equal to this side. Though this is again a crazy integral that we will learn later how to do that. Of course, this requires numerical stochastic integration. So that way we will be moving on. In the coming lectures, we will see some examples. Like the Wiener integral was Martingale, so we can also show this nice property of this Ito integral, which is Martingale property. So our Ito integral is also Martingale, defined in a suitable manner as a process. So I'll define this in a theorem. So the theorem says that suppose you have a stochastic process which is adapted stochastic process, then the process defined by x of t equal to a to t, I mean the Ito integral from a to t of this process dbs for t between a and b is a Martingale with respect to filtration. This ft a less than equal to t less than b. So with respect to this filtration, this process, which is of course the Ito integral of adopted stochastic process, is Martingale. So we won't get into the proof of this as well, because we have already done for Wiener integral. So things will go on the lines of that, but of course there will be some differences. And if anyone is interested to get into the proof, just comment below, we will discuss. So in the coming lectures we will be moving for Ito integrals, but before that we also have got some other property of this, but that we will define in the next video maybe.